Masked pair, or the paired t-test, is the test about the two subpopulations. However, unlike the independent two samples, in a masked pair t-test, there is a one-to-one correspondence between the two subpopulations, and so perhaps this is from the same individual but measured before or after. For example, we might measure their pain level before taking the medication and their pain level after taking the medication. These two observations come from the same individuals, but this is before and this is after. In some cases, it might be a different subject, but they are naturally paired, such as husband and wife, husband 2, wife 2, or twins, twin 1, twin 2, and so on. Because of the matching nature, the sample size has to be the same. So for example, if N1 is the sample size for the sample that come from the first subpopulation, and N2 is the sample size for the sample that come from the second subpopulation, we must have N1 equals N2. From the first sample, we compute the sample mean and we compute the standard deviation. Similarly, we compute the sample mean y sub 2 bar and the sample standard deviation s sub 2 from the second sample. But it turns out that we do not need to compute these statistics as if we were to do it with the independent samples. We record the raw data in the first and the second sample, such as sample 1 and sample 2, and we would have the first observation, we might call it x sub 1, the second observation x sub 2, x sub 3, x sub 4, and so on, all the way to x sub n. Perhaps this is the before data for individual 1, individual 2, individual 3, all the way to individual n. And then we would record the after, the corresponding data or observation after for the first individual is y sub 1, for the second individual is y sub 2, all the way to y sub n. Then we would find the difference. Depending on the purpose, we might take the first minus the second or the second minus the first, but we have to be consistent. For now, suppose we take x sub 1 minus y sub 1 to get the first difference. We label it d sub 1. Then d sub 2 needs to be consistent, x2 minus y2. D sub n, therefore, must be xn minus yn. Again, we need to be consistent. If d sub 1 is y1 minus x1, then d sub 2 has to be y2 minus x2, and so on. What we end up with is only one sample, so we reduce two samples into one sample, where the sample is now the difference. It consists of d sub 1, d sub 2, d sub 3, d sub n. So we have n observations in this sample. Once we obtain one sample only that consists of the difference, we can perform the t-test statistics when sigma is unknown in this case for the one sample. And so we state the null hypothesis. The null hypothesis is the statement of indifference. So we assume that the difference is 0. The null value is 0. And the alternative hypothesis can be either the difference is greater than 0 or the difference is less than 0, the difference in the mean that is, or the difference in the mean is not equal to 0. Recall that in the alternative hypothesis, with the greater inequality, it indicates the right tail test. With the less than inequality, it indicates the left tail test, and with not equal to inequality, it indicates the two-tail test. This is the first step in hypothesis testing, where we state the null and the alternative hypothesis. The second step is to compute the test statistic. In this case, we would compute the t-test statistic. But to compute the t-test statistic for the mass pair, where we reduce two samples to one sample that consists of the difference, we have n values, n observation. Each observation is the difference now. And so with these n numbers, we would compute these statistics. So the sample size here is n, because there are n observations, and with these n values we would compute x bar, but we denote this as x sub d bar for the difference, and we would also compute s sub d, the standard deviation of the sample of the difference. And so t equals x sub d bar minus the null value, but the null value is 0, divided by standard deviation s sub d divided by the square root of n, where the standard deviation divided by the square root of n is the standard error. Then the next step, we would compute the p-value. Remember that the p-value is simply the probability either on the left tail for the left tail test, on the right for the right tail test, or with the two tail, we would need to double the probability from each side. And when we compute the p-value using either a table or a calculator, remember that if we were to use the calculator, the degree of freedom is n minus 1 as usual. N is again the sample size, and we have the same sample size in n sub 1 and n sub 2, so it doesn't matter what number we use. Once we have the p-value, we would compare this with alpha. Alpha is given. If it is not given, we would use 0.05. If p-value is less than alpha, we would reject the null hypothesis, and if it is more than alpha, we would fail to reject the null hypothesis. And then we would make the conclusion based on the comparison between the p-value and the significance level alpha. We always write a statement that would make sense in this case.